Hello friend, one again welcome back to your favorite technical channel EVM Tech Android. So today I am available with a video lecture related to heat transfer by means of conduction, and that video lecture is of 12th number. Again, this is a QR code of my channel. By scanning this QR code directly you can enter into the link and you can subscribe the channel, or in a YouTube you can write EVM Tech Android and you can subscribe this channel. You can see all the video lectures at free of cost. So today we are going to discuss about estimation of error in temperature measurement in a thermometer well. So friend, what we have to discuss today, that is a thermometer well, or you can say estimation of error in the temperature measurement in a thermometer well. This is, you can say, a older topic, or you can say if you go in the industry where you can find very old equipments are available, very old systems are available. In that case, to measure the temperature of the flowing fluid, like you can say the fluid is flowing through this pipeline, if you want to know what is the temperature of this fluid, these kind of thermometer wells are provided, in which we have to put the thermometer, and this thermometer will tell some reading, and that will inform us what is the temperature of the fluid that is flowing through this pipe. So this is a very old technique. Nowadays, friend, you know that thermocouples are available, contactless thermometers are available, or contactless temperature measuring devices are available. So we are not using this kind of system in latest equipment. But if you refer old industry where old equipments are available, or you can say the power plant which are very older, you find the thermometer wells are available, or you can go in any you can say institute where old equipments and instruments are available. You find that this kind of thermometer wells are available, and in which we have to insert the thermometer and we can measure the temperature. This is a very older technique. Nowadays this is not used at all, but the concept what we learn of extended surfaces, this is also called extended surfaces. So these extended surfaces are placed inside the tube, and what is its effect, that we have to discuss. So we are going to discuss about estimation of error in the temperature measurement in a thermometer well. So first we will discuss what is thermometer well, for what purpose this thermometer well is used, then which kind of fluids are used here, why we have to go for this kind of fluid, and all these things we will discuss in the current video. But this is older technique. Nowadays we are not using this at all, but still it is in the syllabus. It is a useful as a part of extended surfaces. We are discussing it again. So the book which I am preferring at present is Heat Transfer by Dr. E.V. Mehta and Professor P.G. Choksi from Books India publication. So this is a very good book, and this is a very reputed publication. You can refer the book for your ready reference. So friend, now let us start with the topic what we have to discuss, that is estimation of error in the temperature measurement in a thermometer well. So first we will discuss what is called thermometer well. So thermometer well is defined as a small tube welded radially into the pipeline through which a fluid whose temperature is to be measured is flowing. Okay, so once again I am repeating, thermometer well is defined as a small tube which is welded radially into the pipeline, through which a fluid whose temperature is to be measured is flowing. The well is filled with some liquid of low specific heat. Very important thing, low specific heat like oil. And the thermometer is deep into the liquid. The heat is transferred to the fluid in a pocket and this temperature is recorded by the thermometer. So the temperature which is recorded by the thermometer, that we are considering the temperature of the fluid which is flowing through the pipeline. So in case of this thermometer well, that is a small tube welded radially into the pipeline through which a fluid whose temperature is to be measured is flowing. So now we will refer this figure and we try to understand what is thermometer well. So and you can see this is a thermometer well. This you can see is a thermometer well. So you can see this is your main pipeline. This is a main pipeline. You can say this is a main pipeline. So in this main pipeline, what we are doing is we are welding or this this welded portion is inserted radially into this pipe. We want to know what is the temperature of the fluid which is flowing here. And to do this exercise, here we have to fill some fluid. So that is having low viscosity like oil. You can see the oil is there. So here the thermometer is inserted. You can see the thermometer is inserted here. It will record the temperature and this temperature which is recorded here, that will be considered as the temperature of the fluid that is flowing through the pipe. So quickly we will go through this figure. You can see the thermometer pocket. The fluid is flowing through this pipeline. D is the outer diameter of this pocket. T, that is the thickness of this well. L is the length of this well. T0, that is the wall temperature. Fluid that is flowing with TA temperature. Ti, that is the temperature indicated by the thermometer. This is the oil. So everything we have discussed. This is the thickness. H is the convection heat transfer coefficient. Ta is the temperature of the flowing fluid. D is the outer diameter of the thermometer well. T is the thickness of the thermometer well. L is, you can say, depth up to which this thermometer pocket is inserted. Ti is the temperature indicated by the thermometer. So same thing is mentioned here. You can see length is so friend, you can see here, as the wall of well or tube or duct is at lower temperature than that of the fluid that is flowing, because the material which we had select has its own thermal conductivity, because of that it has its own resistance, and because of that what is the temperature indicated by the thermometer, that is definitely differ than what is the actual temperature, and therefore the temperature measured by the thermometer will not be the true temperature. So this error in the measurement can be estimated by assuming the thermometer well as a fin or spine or extended surface that is protruded from the wall of the duct in which the fluid is flowing. So what we are assuming here is the fin is of finite length and the heat dissipation from the tip of the fin. So when we will go for x equals to L, we will get temperature variation, that is TL minus TA divided by T0 minus TA, that is equals to 1 upon cos hyperbolic m into L, plus h divided by mk into sine hyperbolic m into L, where m is the fin constant, L is the length of the fin that is protruded, h is the convection heat transfer coefficient of flowing fluid, m is again a fin constant, k is the thermal conductivity of fin material, L is the length of the fin that is protruded, and m is the fin constant. So now the term h upon m k into sine hyperbolic ml, that is we consider as a very small, and hence we are neglecting it. So when we are neglecting it, the approximate distribution is TL minus TA divided by T0 minus TA, that is 1 upon cos hyperbolic m into L, where m, that is a fin constant, and its value is under root of pH divided by AK. P, that is the perimeter, is the cross section area, H is the convection heat transfer coefficient, and K is the thermal conductivity of fin material. So for this cylindrical fin, perimeter is pi d and cross section area is pi dt. So we will get m, that is under root of H divided by KT. And so the error what we will observe in the temperature measurement is proportional to 1 upon cos hyperbolic ml, or you can say that is proportional to 1 upon L into under root of KT by H. So from this equation we can tell that the diameter of the thermometer well is not important at all, or it is not affecting the error in the temperature measurement, because in the previous equation nowhere D was there, and from this equation B it is naturally obvious that in order to reduce the temperature measurement error, m into L value should be as large as possible. So if we want to increase the m into L value, because it is 1 upon cos hyperbolic m into L. Okay, so when we want to minimize this error in the temperature measurement, this m into L value must be higher. So if we want to increase this m into L value, what we have to do is small value of K, means we have to select the material which has moderate or low thermal conductivity such as steel. Second, we have to go for long and thin well. We have to go for long and thin well. So what happens? The pocket that is protruding a small tube may be placed inclined if necessary to provide large insertion of the thermometer, and we have to go for a large value of H value, means we have to put a thermometer where the fluid is flowing with a very high velocity, means here the fluid is flowing with very high velocity. So here we will insert thermometer well, and inside that we have to put the thermometer. So when we will go with this exercise, what happens is the H value is very high here, here the H value is very high, and when H value is very high, what happens is the m into L value that will be increase, so the error that will be decrease. So this was the theory about estimation of error in the temperature measurement while the fluid is flowing through a temperature, or you can say thermometer well. So now we have to refer some numerical. So this kind of numerical may be asked in the internal test, in the university exam, in the competitive exam like UPSC, GPSC, or you can say any technical test of any company in which you are going to appear. So this is a very important concept, but generally nowadays this is not used, but still we have to remember this thing. So friend, now quickly go through the numerical part, that is we'll try to solve this numerical. We'll consider this as a case of fin, and how the temperature is affected or how the temperature is available, that we have to see. So we will consider the first case. The thermometer is placed in the thermometer well that is made up of steel with the thermal conductivity 55.8 watt per meter Kelvin, 12 centimeter long and 1.5 millimeter thick, to measure the temperature of air. The temperature recorded is 84 degrees Celsius. The heat transfer coefficient is 23.3 watt per meter square Kelvin. Estimate the error in the measurement. If the temperature at the base of well is 40 degrees Celsius, means here the air is flowing through the pipeline and we have to measure the temperature. The temperature recorded here is 84 degrees Celsius. We have to find out what is the error in the temperature measurement. So friend, first important thing here is the dimensions are available in terms of centimeter or in terms of millimeter. So first we have to convert this centimeter and millimeter into meter, and what is given in the data, that we have to write. So you can see first convection heat transfer coefficient value is given, thermal conductivity value is also given to us, T0 temperature that is 40, that is also given to us, then T0 40 that is given, TL that is 84, or that is the temperature which we had measured, that is also available. Then what else is given is length is 12 millimeter, we have to convert that into meter. Thickness is given 1.5 mm, we have to convert that into meter, that is 1.5 into 10 power minus 3 meter. So this error in the temperature measurement is TL minus TA divided by T0 minus TA, that is 1 upon cos hyperbolic ml. M, that is pH divided by AK, where P that is the parameter, that is pi d, cross section area, that is pi dt, H that is the convection heat transfer coefficient, and K that is the thermal conductivity of fin material. So the value of M, that is fin constant, that is 16.7 meter inverse, and M into L when we will go, we will get the answer 2. So TL that is 84, that is temperature measured, minus TA divided by 40 minus TA, that is cos 1 upon cos hyperbolic ml, that is 1 upon cos hyperbolic 2. So TA that is 100 degrees Celsius, that is temperature of air which is flowing through the pipeline is 100 degrees Celsius, and the temperature indicated by the thermometer is 84. So the error in the measurement which we can see is TA minus TL, that is 100 minus 84, that is 16 degrees Celsius. So friend, you can see the error in the temperature measurement is about 16 degrees Celsius. So this is very important to find out what is the error that is observed in this case, and we can easily find out what is the error and how we have to minimize this error. So in the same direction, we'll go with one more numerical, that is the oil filled thermometer well that is made up of steel tube. The thermal conductivity, diameter and thickness is given, is used to measure the temperature of steam that is flowing through the pipe. Calculate the minimum length of pocket so that error is less than 0.5% of the applied temperature difference. Take the steam as 250 degrees Celsius and convection heat transfer coefficient is 98 watt per meter square Kelvin. So this is a very important numerical in which it is clearly mentioned that the error is less than 0.05%. It may possible that this kind of task will be given to you and ask you that the error must be less than 0.05%, not only 0.5, it is 0.05%. Then you have to calculate what is the minimum length of pocket required. So this is a very simple numerical. Data is available. Just go with the next slide. What is given? What we have to find out: thermal conductivity is given, convection heat transfer coefficient is given, diameter is given in centimeter, that we have to convert into meter, thickness is given, you can say 0.5 millimeter, we have to convert that into meter. TA, the fluid temperature is given to 80 degree 250 degrees Celsius. Error, that is of 0.5%. So we have to find out what is the length in this case. So TL minus TA divided by T0 minus TA, that is error in the temperature measurement, that is 1 upon cos hyperbolic ml. We want less than 0.5%, that is 0.5 divided by 100. So TL minus TA divided by T0 minus TA, that is 0.5 divided by 100. So you can say this cos hyperbolic m into L, that is 200. Now what is m into L? That is L into m, that is under root of pH by AK. So you can find L into under root of H divided by KT, that is equals to 6, and you can say that is equals to L into under root of 98 divided by 27 into 0.5 into 10 power minus 3, that is length of pocket, that is 70.42 millimeter. So the length of pocket which is available, that is 70.42 millimeter. So when we'll go with this kind of dimension, the error in the temperature measurement is less than 0.5 percentage. So friend, I hope that numerical was very easy, and we will go with one more numerical where we will see some new thing, that is a oil filled thermometer well made up of steel having a thermal conductivity K, that is 45 watt per meter Kelvin. Inner diameter is 40 mm, outer diameter thickness is 1 millimeter thick. So you have to find out what is the outer diameter, that is used to measure the temperature of gas, that is at 300 degrees Celsius. Calculate the temperature of thermometer pocket required. We have to find out what is the length of thermometer pocket required to measure the temperature within 1.8% permissible error. So the permissible error which is shown here is 1.8% only. The diameter of steel tube is 9.5 centimeter through which the fluid is flowing. The tube wall temperature is 100 degrees Celsius and heat transfer coefficient is 93 watt per meter square Kelvin. Means here for the thermometer well, thermal conductivity, inner diameter, thickness, gas temperature is given. The gas is flowing through the steel tube which is of 9.5 centimeter diameter. The error must be within 1.8%. The tube wall temperature is 100. The convection heat transfer coefficient is 93. So almost everything is given, only we have to find out what is the length of thermometer pocket. So let us see. So here you find TA, that is 300, wall temperature is 100, inner diameter is 14 mm, we have to convert into meter, thickness is 1 millimeter, so we can find out what is the outer diameter. Thermal conductivity is 45, convection heat transfer coefficient is 93 watt per meter square Kelvin, permissible error is 1.8%, we have to find out what is the L. So TL minus TA divided by T0 minus TA, that is error in the temperature measurement, that is equals to 1 upon cos hyperbolic m into L. And m, that is a Finn constant, that is under root of pH divided by AK, P that is pi d, area that is pi dt, H is the convection heat transfer coefficient, K is the thermal conductivity. So what is outer diameter? That is inner diameter plus 2 into thickness. So that is 16 mm, that is 16 into 10 power minus 3 meter. Perimeter, that is pi into outer diameter. Cross section area, that is pi dt, or you can say that is pi by 4. Outer diameter square minus inner diameter square. So cross section area is available here, and value of m, that is 46.91 meter inverse. Friend, this calculation of m is very important. If fin constant m is wrong, in that case your entire numerical is with wrong answer, and the unit of m is meter inverse, that is fin constant. So the permissible error is 1.8%, that is 1.8 divided by 100. So TL minus TA divided by T0 minus TA, that is 1.8 divided by 100, that is 1 upon cos hyperbolic m into L. So 1.8 divided by 100, that is 1 upon cos hyperbolic m value, that is 46.91 into L. So the m into L value, that is 4.3053. So the L value which we will get, that is 91.783 millimeter. That is the length of the pocket. So now you can see the diameter here is around 95 mm. This diameter is 95 mm, and the pocket length is 91. So you cannot think I will put the pocket like this. No, it is giving a very high resistance to the flowing fluid, and here the throttling will be observed. So to avoid that and to measure the temperature correctly, what we have to do is we have to put the thermometer pocket inclined. So you can see here this kind of arrangement you have to show into the exam. You have to represent in the front of examiner. You have to represent this thing in front of your boss, or when you are in the company you have to tell your support team, or you can say your boss. We have to make this thermometer incline so that there is minimum throttling and exact temperature is measured with the error 1.8%. So this arrangement you have to show in the exam. So the steam is flowing here, the length is 91.735, where the actual diameter is 95. So we have to insert the thermometer incline, so there is minimum error, or the error in the temperature measurement is within 1.8%. So this was about the lecture related to heat transfer, in which we had discussed a very important concept of fin, where thermometer well is considered as a fin and temperature is measured, which is the fluid that is flowing through the duct or through the pipe. So if you like this video, then do not forget to subscribe this channel and share this channel to your friends, to your you can say relatives, or to the students which really need the help. And do not forget to like this video. This is a QR code of my channel, and the channel name is AVM Tech Android. By searching AVM Tech Android on the YouTube, you can get this channel. All the videos are available at free. You just improve the technical knowledge, and you can share and subscribe this channel. Thank you very much.